So now we want to get into forces of attraction. We've talked a lot about molecules, drawing molecules, putting molecules together. And we've also talked about this idea of polarity, molecules that have molecular dipoles and molecules that don't have molecular dipoles. And that's what's really important here and going forward into this notion of force of attraction. And it's basically, is a representation or represents how a molecule interacts with another molecule of itself. Right? If I have a glass of ethanol, right, there's a lot of ethanol molecules there, right? There's not just one molecule there, there's a lot of them there. And so they're all somehow interacting with one another. And that's what these forces of attraction are going to represent is, how the molecules interact with one another. And that kind of comes back to the notion of the phases that we actually see. Right? We have a solid phase, and if we're going from left to right, we could heat that up and melt a solid to a liquid. I'm changing a phase, a state, solid to liquid, but I'm not changing the molecule. And if I add some more heat, right, I can vaporize the liquid and turn it into gas. So that's the, transformation from solid to liquid gas. I can just add heat and go through, these phases. But I can come back the other direction. Right, I can condense gas to produce a liquid. Or if I cool even further, right, I can freeze a liquid and turn it into solid. So we have the ability to go between all these three states of matter. In terms of forces of attraction, solids have the strongest. Gases have the weakest. And liquids are basically in the middle. And so these phases, and how they exist actually, kind of, start to make sense if you extrapolate a little bit more. Atoms close to one another. Right? That idea of a definite shape. Right? There are strong forces keeping the atoms close. With gases, atoms are not close to one another. Right? They can be compressed. Take up the whole volume of vessel. Right? These are weak forces. And that's because atoms are far away. There's not much attracting them to one another. And then we have liquids in the middle, where, you know, they're close to one another, but they roll over top of one another and all that. But the idea of that, you know, these phases that we see are really a relationship to forces of attraction that are within the molecule. That in the solid state, these forces are really strong, and so that's why we see that molecule exist in the solid state. If those forces are a little bit weaker, well, then we might see that molecule in the liquid state, and then if it's even, you know, the weaker yet, then we might see it in the gaseous state. So that's the nation of what we're talking about in this module, is the idea of going between phases and how that relates to forces of attraction within a molecule. So there's a number of physical properties that we would discuss here. You know, we have the idea of boiling point, melting point, right? And so that's, you know, this idea of boiling point, right? Basically going between liquid and gas. Well, melting point would be, you know, solid and liquid. You know, boiling point is also the condensation point. Melting point is also the freezing point. We have heat of vaporization. And that's specifically going from a liquid to a gas. And then how much heat is involved for that process to go. We also have heat of fusion, and that's going from now a solid to a liquid. Again, we have to apply heat for that process. Very similar in notion to melting point and boiling point as far as these ideas, but melting point and boiling point is actually a temperature, while heat of vaporization and heat of fusion is actually a heat. I know we're kind of on the outskirts of knowing about heat just yet, but some other forces that we tend to look at in terms of these connection between forces and physical attraction or physical properties would be viscosity. You know, this is how fast a liquid travels. Right, water is less viscous than syrup. 6, we can get into then surface tension. You know, that's the ability for a liquid to support mass on top of it. We have capillary action as well. This is how far a liquid travels up a narrow tube. A lot of blood work. Get blood work taken. Use a capillary tube to collect the blood. Same idea. And then the last one here would be vapor pressure. And basically this is, you know, the amount of liquid that is in the vapor state. This is temperature dependent. So just to talk a little bit more about this notion of vapor pressure, just so that we understand what it is. If we have a beaker of water, there's a thin layer of gas that's over top of the water. And that's H2O in the gaseous state. And some of that H2O in the gaseous state is coming down and condensing to make H2O in the liquid state. But at the same time, some of that H2O in the liquid state is coming up and making H2O in the gaseous state. So this is what they would call a dynamic equilibrium. And this layer that we have here of gas, we could refer to as the vapor pressure. If we increase temperature, we find that vapor pressure increases as well. So if I have my beaker still roughly the same amount of water, right now with that increase in temperature, we just find that there's a lot more in that vapor state. And so this is like when you're cooking pasta or you're starting to boil water, right? You actually start to notice steam coming off of the water way before the water actually boils. And that's because you're increasing the actual vapor pressure and seeing that now come off as steam in the gaseous state, right? Because remember, gases fill up the volume of the vessel. So now here is our vapor pressure. So vapor pressure increases with increasing temperature. And the temperature at which the vapor pressure equals the atmospheric. That's the boiling point. So that's why, it really depends on where you're at as far as, how water boils in terms of that boiling point temperature. If you're here in Vermont, we're roughly at sea level, so we're at 1 atmosphere. So we see right around 100 degrees Celsius. But if you were to go up into the mountains, up in Denver or Colorado, and now you're a mile up or even higher, water's boiling point is actually lower than 100 degrees Celsius, because now you're not at an atmosphere of 1 atmosphere in terms of atmospheric pressure. You're actually at an atmospheric pressure lower than 1 atmosphere. And so you'll still see the same observation. You'll still see water boiling. But if you were to take the temperature of that water boiling, it would be actually less than 100 degrees Celsius. So just a rehash of vapor pressure there. But these are the forces, these are the physical properties that we're going to be talking about in terms of, their effect on, their effect that they have on these forces that we're going to be getting into right now. I think the most important thing to remember here is that the greater the physical property, the stronger the force. This goes for all of 1 through 7 above. Vapor pressure is the only one that's opposite. Meaning that, stronger force within a molecule would be synonymous with lower vapor pressure. So, we're going to be talking about these forces, and we'll do some comparisons, but realize it's just a question of if we're talking about the strongest force, right, that one would have the greatest melting point, the greatest boiling point, the greatest capillary action, right, the greatest heat of vaporization, etc., etc., etc. Except for vapor pressure, it would have the lowest vapor pressure. So let's talk about our forces. We have 5 of them that we're going to be looking at. We have electrostatic. We have network covalent. We have hydrogen bonding. And we have dipole-dipole. And then lastly, dispersion. So these are the 5 forces that we are going to talk about. We find that they're somewhat ordered in terms of strength, but there are subtleties as we go into them as well. So let's start off with one and then just go forward through all of them. So electrostatic forces basically result from opposite charge attraction. It's really looking at Coulomb's law. Between basically a metal and a non-metal. Really what we're talking about are ionic molecules. Ionic molecules have electrostatic forces. This is one of the strongest forces. This is why, most ionic molecules exist as solids, is because it's one of the strongest forces out there. And there is a relationship between ranking these ideas of electrostatic forces in terms of comparison. And so elements of greater charge in an ionic molecule produce greater electrostatic forces. And then if elements are of the same charge, in an ionic molecule, then the elements that are smaller produce the greater electrostatic force. So we have kind of, an A and a B, if you will. But you want to first look at the first address and then go to the second, meaning first look at charge and then look at size. So as an example, we could say, which has, stronger electrostatic forces. And we could say potassium chloride versus magnesium oxide. And so the first thing I would want to do is look at, is there a charge difference? And here I definitely see a charge difference with the potassium wanting to be +1, the chloride being -1, the magnesium being +2, the oxygen being -2. And so because of that, right, higher charge is equal to stronger force. And so that would be the magnesium oxide. Could ask a very similar question, right? Same idea, stronger electrostatic forces. And look at sodium chloride versus lithium fluoride. And so we want to kind of do the same thing. Is there a charge difference? Right? And in this particular case, right, we would say no. Right? We have +1 and a -1 for both the metal and the non-metal. So then we go to size difference, which there always will be. But you only go to it if your number, your first part of it, the charge part of it, is actually no. So now we could say, well, smaller atomic radius is equal to the stronger force. And so that's why we would have lithium fluoride, right? Lithium is smaller than sodium. Fluorine is smaller than chlorine in terms of the idea of size. So that's the idea with electrostatic forces. Electrostatic forces is some of the strongest forces out there, and every ionic molecule has these electrostatic forces. So it's actually the other reason why we see a lot of these in that solid state in our planet, right, as far as 1 atmosphere, 25 degrees Celsius, et cetera, et cetera. The second force of attraction is network covalent. And basically this is a large lattice or a large array of covalent bonds. Right, this is, similar to ionic in that ionic molecules are arrays of ionic bonds, right, in that sense of an array. Diamond is a great example. Diamond has these perfect, tetrahedrals, and each carbon that's attached to a carbon within this structure is attached to another carbon, which is attached to another carbon, right? Which is attached to another carbon. So we just have this, vast array of carbon atoms that just keep going and going and going. Right, and so we could kind of say, well, it's just like this big, repeating unit going off, into the distance as far as diamond is concerned. So it has very similar attributes to our ionic system, is that this is also one of the strongest forces. We can't compare it to, other network covalent molecules and or electrostatic molecules. In terms of strength. But network covalent is stronger than the other three. As far as the ones we haven't gotten to yet, hydrogen bonding, dipole-dipole, and dispersion. So, it's just kind of tough with the structure. There's more to it than just simply looking at how many elements are there. And so we can have really strong forces of attraction within an array, like we see with diamond. I mean, diamond's used to tip saw blades to cut through concrete, et cetera, et cetera. There are also other types of macromolecular structures that don't have the same strength in terms of the force of attraction as diamond does, right? So we can have all different levels, and it's really hard to relate network covalent to network covalent. It's also very hard for us to relate network covalent to electrostatic or network covalent to ionic. There's no system here for that. So all we can say is that, network covalent is definitely stronger than the other three that we have coming our way, as far as hydrogen bonding, dipole-dipole, and dispersion. A good way to recognize, network covalent is the idea of, a large molecule. So we could have something that maybe looks like this. Where we have, a large repeating unit. In terms of that nature. So here we might have like a plastic or something like that has network covalent forces. And we just have this repeating unit of CH2O in the middle. But eventually that makes us a very, very, very large molecule. And so that's our network covalent, looking for, the indication that there is a very large molecule I'm dealing with. The third one is hydrogen bonding. And hydrogen bonding is, a through space attractive force between an oxygens or nitrogens, lone pair, and a polarized hydrogen atom. Polarized meaning we would have some type of positive charge on that hydrogen atom. Of another molecule. So, water is our best example of hydrogen bonding, where here we have our water molecule somewhat drawn in the tetrahedral, and if we maybe draw another one or two of these together, we might be able to start to see this attractive force. Right, so here's a bunch of H2O molecules, and if we look at the H2O, right, we have a delta minus, which is the oxygen, and then each one of these hydrogens is actually polarized because of the differences in electronegativity that we have. And this is the hydrogen bond. And it's really a misnomer. It's not really a hydrogen bond. It's hydrogen bonding. It's a force of attraction. Right, this is an attractive force that we actually have. So, to recognize molecules with this feature, you want to look for, OH within a molecule or NH within a molecule. These, I guess you could call subgroups, love to hydrogen bond. Also, the more OH and NH you have, within a molecule, the stronger the hydrogen bonding forces. So that's just has to do with how many hydrogen bonds you can actually make. So if you were asked as an example, which has the greatest capillary action, and you have here methanol and glycol. So we could see from this recognition here that, we have, hydrogen bonding. But if we look at our molecule on the right, we actually see two sets of hydrogen bonding. So, more hydrogen bonding functionality, right, is going to equal the stronger force. And since we're looking for greatest capillary action, we're looking for the strongest force, and so that would be the one with the 2 OHs. Hydrogen bonding, is weaker than electrostatic and network covalent. But is stronger than the last two, than dipole-dipole, and the last one, dispersion. The fourth is dipole-dipole. And this is an attractive, through space force between molecules' polarity, right? They're molecular dipoles. So if we look at an example of, let's say, acetone, looks like this. And we can have a few of them here, kind of in a line, and from this, difference in our bond dipole that we see for the carbon-oxygen bond, right? Our carbon is partially positive, our oxygen negative, and so we have, this molecular dipole, right, pointing to the left as far as how I've drawn it here. And so it's that molecular dipole which now kind of creates this idea of a tiny magnet, where these molecular dipoles, are attracted to one another. Same thing with the hydrogen bonding, right? It's kind of this attractive force between something negative and positive, right? This idea that we have this Coulombic attraction between plus and minus, or opposites, attract. So we have, the same, dipole for, each one of these acetone molecules, right? They're all the same molecule. And as a result, there's this through space attractive force now between the negative part of the molecule and the positive portion of the molecule. And so our through space attraction is right here. Right, and so that's what creates that force of attraction is that permanent dipole that we have between the carbon and oxygen, creating now a molecule with being being polar, that they're attracted to one another in that regard. Dipole-dipole forces of attraction increase with basically increasing molar mass. So if we had an example of, asking, which one has, the greatest viscosity, and we could look at CH3Cl versus CH2Cl2. Well, they both have, a dipole, right? If we were to draw these out, rather quickly, we could have showing this tetrahedral, right? We have a molecular dipole here pointing up. And then we have, the same thing going on with the dichloro version of our methane here. But we have a much heavier mass. And so here would be our dipole here would be kind of maybe going up like this. So then it looks like that. And, so it's not a relation to the dipole, just a relation to molar mass. So that greater molar mass is stronger dipole-dipole attraction. So that's dipole-dipole. The last one is dispersion. And this is an attractive through space force between molecules that do not possess molecular dipoles, right? Or we had the symbol, of that for that representation. This interaction occurs through this notion of instantaneous dipoles. These don't exist very long. We could say that they are, fleeting. And so as an example of that, I can maybe show helium, where we have, helium with its 1s, and we have two electrons, right, somewhere in that 1s, and now we're showing how it's interacting with other helium atoms. And so what we find that occurs is that notion of an instant dipole, where our helium atom will have those two electrons on the same side, right? It's a probability, it's a possibility. And that sets up the notion of an instantaneous dipole. And so that is what we find is interacting in terms of now the dispersion force of attraction that's going to cause basically a fleeting dipole or an instantaneous dipole in another helium atom. And there is our dispersion force of attraction. And so when we look at, a lot of gases tend to possess this as their force because it's actually generally the weakest of the bunch. Dispersion forces increase with increasing molar mass as well. So if we have, for instance, two different molecules here, let's say, which one has the highest boiling point. And we could say, well, helium versus carbon dioxide. Well, both of these are, dispersion molecules, right? Helium is monoatomic. So, it has no, molecular dipole. And our carbon dioxide as well is, non-polar. So we have something that looks like this, and it also fits that bill for the same type of polarity. But if we compare, molar masses, where we have, 4 grams per mole there and 44 grams per mole, right? The CO2 has the stronger force, right? So both, our dispersion. So, the larger molar mass is equal to then the strongest or the stronger force that we see above. If the molecules have the same molar mass, then the molecule with greater surface area will have the stronger force. So if we were to compare, maybe ask, which has the greater viscosity. And so we have here, butane pentane rather, and isopentane. If you calculate these have the same formula, have the same number of carbon and hydrogens, i.e. they have the same molar mass. But if we look at surface area, we have a greater surface area with the extended chain as opposed to the tight-fitting structure. So, we're have the idea of, the same, molar mass, so greater surface area is now equal to stronger forces. So that is the last force, but we still have a little bit more to talk about in terms of the last two comparisons. In terms of the dipole-dipole and the dispersion. So normally dipole-dipole is definitely the stronger of the two when comparing dipole-dipole to dispersion. The idea of comparing, a permanent dipole to a, instantaneous dipole, kind of, backs that notion up. However, this is, a molar mass game for both forces of attraction. So, if your dispersion molecule is significantly, heavier in terms of molar mass, so, and that roughly significance is 20%. So if your dispersion molecule is significantly heavier than the, dipole-dipole molecule, then dispersion will be stronger. And hopefully you get that notion just like thinking about, nonpolar molecules like, propane and butane, right? These are 3 carbons with propane, 4 carbons with butane. They're both gases. As soon as we add a 5th carbon and make pentane, now that's actually a liquid. So we see going between this phase of gas where we have weaker forces of attraction compared to something now that's heavier, still dispersion forces, but now we know we have stronger forces because we're not in the gaseous state anymore. We're actually in the liquid state. And then we can keep going all the way up, right, to get to very large molecules that contain carbon, such as motor oil or tar, right, and things of that nature. And we can see how adding more and more carbons leads to greater and greater viscosity as we go through it as well. So there's definitely this molar mass game that we have to play. And it's really roughly this 20% idea. So to do maybe a couple examples of that, right? We have here, for instance, let's ask the question of which has the greater surface tension. And we'll ask, bromine versus chloroform. And so when we look at now two different forces of attraction, right, we just want to, be slow and stepwise in our production of, okay, well, what's bromine look like? Let's, ascertain, okay, that's a molecule that has dispersion forces. And then if I look at my chloroform, I see I have a dipole. Right, so that's dipole-dipole. And so in that comparison, right, since we are comparing dispersion and dipole, right, it is still a molar mass argument, right? So bromine would weigh 160 grams per mole, while chloroform weighs right around 50 or 50.5 grams per mole. So there we see a drastic difference. Roughly 3 times greater in terms of molar mass. And so that's why our bromine would have this greater surface tension. So the Br2 is greater in mass by roughly 300%. So it has the stronger forces. We can do another example here with looking at which one has, I guess, the greatest melting point. And so we would look at maybe this as an example, phosphine and silane. If we look at these molecules, we have a dipole in terms of our phosphane. And if we look at our silane, we find that we would have no molecular dipole. So again, the comparison between the two, dispersion and then dipole-dipole. If we calculate the molar masses, we find that these are pretty much identical. And so since, very close in molar mass, the dipole is stronger. And so the phosphine would have, the stronger forces of attraction that exists. So that's this notion of forces of attraction. And, we would be looking at, examples that might look like this in terms of a comparison. Saying, which has the greatest melting point. And we could look at sodium chloride versus oxygen versus ethanol. And, your first step is just to identify forces. And then your second would be to apply our rules. So we have electrostatic for the sodium chloride because we have the +1, -1 system, metal, non-metal. We have O2. Right, and that would fit under dispersion. We then have methanol with that OH, so there's our hydrogen bonding. And if we apply the rules, electrostatic is the strongest. And so that is our answer. Right, so that's the idea. We could actually rank these and say that, well, sodium chloride would be the greatest, then methanol, then oxygen, in terms of melting point, because of these forces of attraction that we just discussed. So to summarize, in terms of forces of attraction, we have, 5. We have electrostatic. With electrostatic, remember we have a, greater charge equals stronger force. And then B, we have, smaller size equals stronger force. That notion is really involved with lattice energy. Another form there, looking for the metal, non-metal, recognition. The second one is network covalent. And here we were looking for, something that has, a large, kind of repeating unit. Something like that. I guess I'll change that R to just a CH3 group. Well, we see that repeating unit. And these are the strongest. We then have one, in the middle, which is our hydrogen bonding. And with hydrogen bonding, remember we're looking for here, this idea of having an OH or, an NH within the molecule. These being substructures. within. Two electrons there on the nitrogen. And hydrogen bonding is stronger than the last two, which would be, sorry, I got my numbering out of order there. Third is hydrogen bonding, so we're number 4 here, which is dipole-dipole. For dipole-dipole, remember we're looking for that permanent dipole for a molecule. Or a polar molecule. And then the last one is the dispersion. Where we don't have a permanent dipole. And this would be a non-polar molecule. And so remember with these, it's generally ranked in order, but for dispersion, if dispersion is heavier in molar mass by 20%. And I'll try to make that more obvious. %20 is kind of a harder one to kind of figure out on the fly. But if dispersion is heavier in molar mass than by 20%, then dispersion is stronger. So we have, that relationship to strength of the force of attraction to then, these physical properties that we were talking about. So that is forces of attraction.